Hi. This third presentation in the Groundwork playlist will revisit operators and data types, and we will also look into typecasting. At the end, you should be able to explain the relation between data types and packages, and also what is typecasting and why it is necessary. We will follow the same sequence during the presentation as indicated in this slide. Let's start with operators and data types. The IEEE standard defines an object as something that contains a value, and a value has a type. Consider a signal, for example, which may be present at any given port. We have already seen that inputs and outputs are normally defined as standard logic. And we will see that standard logic vector is also frequently used when dealing with buses. Besides understanding the meaning of the data type associated to any signal, it is also important to understand which operators can work on it. A full description of data types supported by VHDL and of what operators can be used with each one is outside the scope of this introductory presentation, and truly speaking, it might be quite boring. Practice will tell us a lot with this respect, and meanwhile you can Google meaningful expressions to find out more about it, such as VHDL data types or VHDL operators. Looking into the two most commonly used IEEE packages will also tell you a lot about operators and data types. You already know that standard logic and standard logic vector are pre-declared in the IEEE Standard Logic 1164 package, and mention has been made to the numeric standard package, which pre-declares the unsigned and signed data types and states how certain operators defined for Standard Logic 1164 data types work on the new data types of numeric standard, something that is known as operator overloading. You may recall that the standard logic data type comprises 9 values. It belongs to the enumerated type class, which also admits user-defined data types, as we will see later. In this course, we will only use the 0 and 1 values, but any standard logic signal may take any of the 9 values shown in this slide. Please Google the standard logic type values expression to see a full description. We use this type all the time, yet we don't need to declare it if our library section comprises a use clause invoking the standard logic 1164 package. From that moment on, we are able to declare signals of the standard logic type and to work on them using a variety of operators, such as we have done in the case of the 2 to 4 decoder circuit. You should be aware that there is a wide variety of data types besides standard logic vector, unsigned, and signed. Bit and bit vector, for example, are also enumerated data types, but in this case supporting only 2 values, 0 and 1. May I ask you to try to find out what IEEE library package declares these 2 data types? That same package will also declare the other data types seen in this slide. Let's talk now about typecasting. You have already been told that not all operators work on all data types. In addition, for example, does not work on standard logic, but you will frequently need to use arithmetic operations. In the case of a counter, for example, your outputs will most likely be declared as standard logic vector, and counting up is normally done by adding 1 to the current counter output value. In such cases, you will need to convert the original data type into another type that supports the operation that you wish to carry out, and then to convert back. This is known as typecasting, and it is frequently used in VHDL design. It is also a frequent source of problems, either because you forget that typecasting is needed or because you try to perform illegal typecasting operations. Practice will be of great help with this respect. Considering a specific example is a good way of learning. This slide shows the VHDL code to design a 4-bit header. You may have noticed the concatenation of a 0 to the left of the two operands in order to match the number of bits of the result. But what I want to emphasize in the statements highlighted in red is that we have to convert the standard logic vector type of the two inputs into unsigned in order to support addition, and then to convert the result back to standard logic vector in order to allocate its value to the output port. The unsigned signals used did not exist before, so they had to be declared, as shown immediately below the architecture clause. Keep in mind that the mismatch between data types and operators working on them is a frequent source of problems, so it may help to look for this kind of reasons when you come across problems in your code. And that's it for now. Thanks for your attention.